Hello, everyone. I'm Dana Shamir. I'm going to talk about non-interactive universal arguments. This is a joint work with Nir Bitansky, Omer Panet, and Tomer Solomon. So I will start with the most basic notion in this talk that we already saw today a lot, which is succinct arguments. So succinct arguments is simply a proof system for some language in NP. And we have the standard properties of completeness and computational soundness, where in computational soundness, I mean soundness holds against the polynomial adversary. And the reason it is succinct is because of the efficiency, which is also called double efficiency. So the prover runs in time polynomial in the input, which means it's enough for the prover to determine the language. And the verifier runs in time linear in the input. So it needs the help of the prover in order to decide the language. Okay, so this is a succinct argument, and it is a central concept in cryptography. Many different notions are being studied, and in this talk I'm going to focus on one influential notion, which is universal arguments. So universal arguments were introduced by Barak and Goldreich, and in one sentence the idea is that if we use succinct arguments for any language in NP, we can construct a protocol to prove this language. But what if we want one proof system to prove all languages in NP at once, together in the same protocol? So to say what it means more formally, first we need to define the language that our argument is going to prove. And this is the universal language. So intuitively, it contains all non-deterministic computations. And what I mean by that is that it contains all non-deterministic Turing machines, inputs to the Turing machines, X, and some time T, such that M accepts X within T steps. Okay, so this is the universal language. And now, note that any computation in NP, this language covers, okay? I can write any computation in NP in this way using a non-deterministic Turing machine. But there are also some more computations in this language. As you can see, T can be anything. It can also be super polynomial, okay? So this language isn't in NP. Yes, so this language isn't in NP, and so we can't use succinct argument as is to prove this language. And so these are universal arguments, so is simply an argument to prove the universal language. So it is the same drawing that we had before, only now the instance that we work on is an instance to the universal language of the form mxt.
Wait, can you comment on why the language is not an NP?
Yes, so so T here doesn't have to be polynomial. Okay, I can't give you in advance some polynomial bound on all of the T in this language. And if I want to decide what you could suggest is, okay, let's suggest the computation that runs M non-deterministically on X for T steps. But I don't have a polynomial bound on T. So this computation isn't necessarily polynomial.
Why can't you use like a unary representation of T, like
right,
1 to the T?
Then that would be the
What did you suggest?
Yeah, like why can't you use like 1 to like unary instead of like a binary string? You put like a unary representation. It's like 1 to the T. Then it's an NP language.
Yes, I can do that.
But then the prover is always going to run in polynomial time. So what does that imply on like the values of T, which we can actually prove in this?
So actually, what I was about to say is we allow the prover to run in time polynomial in T, in the computation time. Okay, so the prover can decide the language.
Okay.
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 So yeah, so the universal argument is an argument for the universal language. And when I talk about double efficiency now, I say that the prover runs in polynomial time in T. Okay, so the prover can decide the language, and the verifier, it's complicated, but it runs in time polylogarithmic in T. So it's succinct, it can decide the language on its own. And we have the exact same properties of completeness and computational soundness. And now note that computational soundness holds against polynomial adversaries, where the lambda here is the security parameter. We can think of it as it is the size of the input x, and so yeah, so soundness holds against polynomial adversaries. And I just want to emphasize here that the adversary of polynomial size, it can claim any statement. It can even claim a statement with T that is super polynomial. Okay, so we have an adversary that our adversary might try to make statements that it can't even compute. Okay, so this is an interesting, something interesting here, and you will see it later when we try to construct a universal argument.
So what is the relationship between lambda and T? Is there a relationship?
So we take T to be less than 2 to the power of lambda. So this is a universal argument, and as I said, this is going to be our central topic in this talk. So why is it important? To explain why it's important, let me just emphasize the differences between a succinct argument and a universal argument. So if I use a succinct argument, for any polynomial upper bound on T that you give me, so for some fixed polynomial, I can give you a proof system for this type of computations, okay? But if I use a universal argument, I can give you a proof system for any T at once, okay? So that's the main difference. And let me give you 2 examples where it is useful. So the first example is Barak's zero knowledge for non-black box simulation. And this is actually, this was actually the original motivation for all of this work on universal arguments. So in short, in this protocol, the prover tries to prove to the verifier some claim that depends on the verifier's code, okay? And when I construct the protocol, I don't know in advance what is going to be the size of the cheating verifier. And that's the reason I need here a universal argument. Another important example, which was just mentioned before, is the incrementally verifiable computation, where I want to compute a very long computation, and I want to be able to prove it one step at a time while the computation is taking place. So as you can see, while I'm starting to prove the computation, I don't know in advance, I don't know what T is going to be. And it's I already started running the protocol and I don't know what T is going to be. I don't have any idea if there is some bound on it. So this is also an important example. Okay, so we talked about universal arguments. Let's see what we know about them now. So first, about succinct argument, let me tell you what we know first about succinct arguments. So there is the classic result of Kilian that construct for any language in NP, it gives a succinct argument, assuming collision resistant hash. Okay, so we have this result, and we can start asking now if it's universal. What about universality in this result? So if we look carefully, we see that it is universal, but in some weak sense, okay? So I can use this protocol to prove any computation, but I need to know in advance some upper bound on T bar. And then I also need the collision resistant hash to be secure against adversaries of size polynomial in T bar. Okay, so why did I say it's a little weak? So as I said before, the universal language also contains super polynomial computations. So if I try to find some matching T bar here, I get that my collision resistant hash has to be secure at least against super polynomial adversaries or even more. And the questions we ask when we talk about a universal argument is this inherent? Do we really have to assume super polynomial assumptions? And it seems like maybe it isn't, maybe we can skip it because as I said, we only want our argument to be secure against polynomial adversaries. So actually, yes, this was the state of affairs when Barak and Goldreich started working on universal arguments. And yes, they showed that you don't need to super polynomial assumption. So we can construct a universal argument for any t, and our assumption only needs to be secure against polynomial adversaries, which is just the standard collision resistant hash, the same that we had for a succinct argument. Okay. Right. So we have a universal argument. But what I didn't tell you till now is that both these protocols require 4 messages. And as we already discussed today, there are many works on trying to get rid of interactivity in many settings. And this is our question today too, whether we can make the universal argument non-interactive. And if you think about it, in the example that I gave before about incrementally verifiable computation, it is very important that the proof will be non-interactive. Okay, so this is our question today. Are there non-interactive universal arguments? Okay, so let me go back to the beginning and just say what is a non-interactive argument. Again, it's very similar to succinct argument. It is a succinct argument, only now the prover just sends one message to the verifier. And the verifier, according to this one message, decides whether to accept or to reject. And as we saw today, in the succinct non-interactive setting, we need to add a common reference string that both prover and verifier know. Now we have the same properties of completeness and computational soundness and efficiency. Okay, and so this is our non-interactive argument. Note that the setting that I show here is a publicly verifiable setting. There are also works in the setting of a privately verifiable setting. And today I'm going to focus on the publicly verifiable, but our results work for both. Okay, so yeah, this is a non-interactive argument. And as we saw before, in the interactive arguments, we can define universal non-interactive argument that just proves the universal language. Okay, so now I want to tell you what we know about non-interactive arguments. And so there are tons of works about non-interactive arguments for non-deterministic computations for languages in NP. And they're from non-standard assumptions or heuristic assumptions. There is also a line of works on non-interactive arguments for deterministic computations, what's called SNARGS for P. And today I'm going to we will go in this direction, okay, of the non-interactive arguments for P. Okay, so let me tell you what we know about them. So under polynomial assumptions, we can construct SNARGS for P, assuming LWE or dealing. Okay, so now, again, I'm going to ask the same questions that I asked in the interactive setting. What about universality? If I look at these constructions, can I use them for universal arguments? So actually, you get pretty much the same thing. And so I can give an argument for all computations, but I need to know in advance some upper bound T bar on T. And again, in this case, my assumption is has to be secure against adversaries of size that depends on this T bar. Okay, so, oh, yes.
Sorry, like probably I'm confused. Like under polynomial assumption, you mean like a single assumption that's secure against like all polynomial time adversary, like for
Yes.
every n to the c, every c?
Yes, exactly. So I mean, specifically, I mean LWE or dealing, and I want the security of it to hold against polynomial adversaries, and this is actually the standard assumption. So when we assume LWE, this is what we assume.
So it's not like fixes constant and secure against like n to the 100 time adversary.
No, it's not a fixed polynomial. Yeah, it can be any polynomial. But this construction doesn't give this assumption. It doesn't give a snark under this assumption. It needs an assumption that might be stronger. It might be super polynomial, even some exponential. Okay. And so, yeah, I asked the same question in the non-interactive setting. Can we give a snark for any computation while we only assume an assumption that is polynomially secure? Okay, so yeah, this is the question that we try to answer in this talk. And now let me tell you about our results. So our main result is constructing non-interactive universal argument. And what we need to assume is LWE dealing, which is a polynomial assumption. It's the same assumption that we saw was used to construct a succinct argument, a non-universal argument. And we add an extra assumption of fully homomorphic encryption, which I remind you, it depends on LWE and on circular security. And we also need a mild worst case complexity assumption, and I will explain it in more detail in the next slide. Okay, so this is our result. This is how we answered the question that I just asked. And now I want to tell you a little more about the results. So actually, we give a few different results where they are mostly the same, mainly they're the same thing, but we have some different notions of soundness in each result. So in each result, we also need different assumptions. So if we only need a non-interactive universal argument with uniform soundness, so soundness only holds against uniform adversaries, all the assumptions that we need are LWE or dealing, the assumption of the succinct argument, and FHE. Okay, we don't need any complexity assumption. Now, if we want a non-interactive universal argument with full soundness, soundness that holds also against non-uniform adversaries, we need to add an extra complexity assumption, which means, so intuitively, it means that circuits of fixed polynomial size can decide all P. There will be some language in P that the circuits cannot decide. And more formally, for any constant C, if we look at all circuits of size n to the power of C, there is some language in P that they can decide infinitely often. Okay, so this is our complexity assumption. And again, we consider it mild. And another result we have is we extend the previous result about universal arguments to the setting of incrementally verifiable computation. And in this case, we need the same assumptions, only the complexity assumption requires some, has also a space requirement. Okay, so we can't speed up computations with non-uniformity, even if they are bounded, if their space is bounded. Okay, so this is the. But again, both these assumptions we consider mild, and for example, they follow from non-uniformity H. Okay, So, yes.
Sorry, slightly. Assuming LW against like non-uniform adversary, don't you get like those assumptions automatically?
Sorry, what's the question?
Like if you assume LWE with like non-uniform security, like then it should follow, right?
What is the question?
Like if sorry, like if you assume LW with like non-uniform security, it's like why those two assumptions follow?
You mean the complexity assumptions?
Yes.
Why do you need them in the non-uniform case?
Is it because they're making polynomial LWE assumption instead of sub-exponential?
Sorry, I can't hear.
That LW is secure against non-uniform polynomial attackers.
Sorry, so no, that won't be enough for us. We'll see later in the construction that just assuming LW is not enough for us. We need something extra. And this something extra, we don't need it in the uniform case. Okay, we don't need to assume this if all we need is soundness against uniform adversaries. But if we want soundness against non-uniform adversaries, we will have to assume that we will see in the construction where it comes in.
Yeah, LW is not a such type. Yeah.
Yes. Yes, I need the CRS. Yes. Okay. And so now that we saw the results, let me explain you about some main theorem that we have behind all of these results. So the way we show it, the result that I now talked about, is we take SNARGS for P that I already mentioned before, the constructions that we have for it, and we lift it into universal arguments, which is what we want. The way we lift them is we use a cryptographic tool, which is Cryptographic Puzzles, and I will explain later what exact puzzles we need. Okay, so this is what we're trying to show. And actually, I wasn't very accurate, so SNARGS for P isn't enough for us. We need something a little stronger, which in this work we call semi-universal arguments. And what I mean by that, it's an argument that can prove any computation, but soundness is only guaranteed if I have some fixed polynomial upper bound on the computation time t. Okay, so I take the semi-universal argument and I lift them into a universal argument where soundness is guaranteed to any t, even t in the size of 2 to the power of lambda.
So, I'm sorry, in the bottom, where is it? What is the poly lambda? Is it like lambda squared? Is it fixed ahead of time? Or?
Yes, it needs to be fixed before we construct our.
So can it just be lambda squared? If it was just lambda squared, would you be able to lift it, or do you need to be able to say, you know, for any polynomial there exists an argument?
No, yeah. So it's the second.
It's
so
the second one?
for any polynomial, yeah, there exists a proof system if t is bounded by this polynomial.
Okay.
Yeah. Okay, next. So why is it okay to assume semi-universal arguments? Because actually, as we saw before, the existing constructions that I mentioned for SNARGS for P, they actually are a semi-universal argument. Okay, so we take what already exists and we try to lift it into a universal argument. And again, we need to assume that soundness is, we need an argument where soundness is guaranteed when t is bounded by some polynomial, and we lift it into an argument where soundness is always guaranteed to anything. So before we see the construction, let me explain a little bit why the existing constructions aren't universal. So suppose we have an adversary of polynomial size, and it tries to claim some statement nxt. We'll focus on the case that it tries to make a false statement. So what the existing constructions do is they construct a reduction that uses this adversary to break their assumption, LWE or dealing. Okay, so now it turns out that the reduction size obviously depends on the size of the adversary, but it turns out that it also depends on t. So actually the reduction needs to make the computation on its own. Okay, and this is where the problem comes in. So if t is not bounded by any polynomial, this the reduction that we got is not polynomial. And then if we try to break LWO dealing with it, if it's just a polynomial assumption, it doesn't do anything. So that's the reason we needed to assume something stronger. Okay, so yeah, this is the problem. The reduction size depends on t. So let me explain how we solve it. So what we will actually want is that the reduction size will only depend on the adversary size. And the way we do it is we want to make sure the adversary doesn't try to make statements that it can't compute. Okay. So if the adversary only makes statements that are approximately on of the size of the adversary, then we have a polynomial upper bound on t. Okay, so the way we do it is that we ask the adversary when he tries to prove some statement to also prove that he made a t-long computation. And if the adversary made a t-long computation, it means that t is actually no bigger than the adversary, and then the size of the reduction is polynomial.
One quick question.
Yeah.
Does it mean the size of the code that generates MST or the runtime of the adversary?
The runtime of the adversary. I mean the size of the non-uniform adversary. Yeah.
Okay, okay, makes sense. Thank you.
Okay. So how can the adversary prove that it made a t-long computation? That's where the puzzles come in. So so we ask the adversary to solve a puzzle that is t-hard. Okay, we'll see later exactly what is this puzzle, but intuitively it means that if the adversary solved this puzzle, then it must have made a t-long computation. So that's the idea behind our construction. And now let me define the cryptographic puzzles that we use. Okay, so when we think about our cryptographic puzzles, we imagine that there is some challenger and some solver. The challenger gets a parameter t, a difficulty parameter, and it sends to the solver a puzzle instance z. And the solver needs to solve it. It sends back the solution, and then the challenger can verify. Now, there are different notions of puzzles in the literature, for example, time lock puzzles and proof of work. And what we are doing is we assume we use the simplest puzzle that is enough for our requirements. So let me tell you about the properties we need from this puzzle. So first we need completeness, which means that there exists some solver that will solve the puzzles in time approximately t. And we want fast sampling and verification. So the challenger here that samples the puzzle and then verifies it is of size only log t. Okay, it doesn't need to be able to solve the puzzle on its own. And note that the verification here is public. The challenger doesn't need to remember any state about the puzzle in order to verify. And of course, we want the puzzle to be hard, so we require soundness, which means that a solver that is significantly smaller than t cannot solve the puzzle. Okay, so epsilon here is some gap. So if I have a solver that is smaller than t to the epsilon, it won't be able to solve the puzzle. So these are our cryptographic puzzles. And now let's see the construction and how we use them. Okay, so as I said, we start with a semi-universal argument. So the prover sends to the verifier some proof. And as I said, in the semi-universal argument, soundness only holds if t is bounded by some polynomial. Okay, so how do we make this universal? That's where the puzzles come in. So we add to the CRS lambda puzzle instances of increasing difficulty, where the ith puzzle is of difficulty 2 to the power of I. And then we ask the prover to solve the puzzle log t, which is a puzzle of difficulty t. And intuitively, if the prover solved a puzzle of difficulty t, it had to run time t at least, which is what we needed. Remember from the idea, we wanted to make sure that the adversary doesn't make a statement that it can't compute. Okay, so now let me explain to you the idea around how we prove soundness here. So assume we have some adversaries of polynomial size, and it tries to make a statement, a false statement, mxt. So now, if the size of the adversary is smaller than t to the epsilon, it's the puzzle's epsilon, it means that the adversary shouldn't be able to solve puzzle of difficulty t. And then we can use this adversary to break the soundness of the puzzle. On the other hand, if the adversary is bigger than t to the epsilon, then note that we have a polynomial upper bound on t. And this is a fixed polynomial upper bound. It only depends on the adversary size. So in this case, we can just use the soundness of the semi-universal argument.
How do you distinguish these two cases?
So yeah, yeah. We distinguish them. We need to do it when we prove, but we don't need it while the protocol runs. Okay, so that's our construction. Now what's left for me is to explain how we construct the cryptographic puzzles. Okay. So here the idea is that we start with some problem that is t hard in the worst case, okay? And we have to assume that something is hard to get a hard puzzle, but not that this is a mild assumption, just the worst case hardness. And we lift it into cryptographic puzzles, where in cryptographic puzzles, we can sample puzzle instances from some distribution, and then a solver that is significantly smaller won't be able to solve the puzzles with high probability. Okay, and the way we do it, we use here is where we use fully homomorphic encryption. And actually, we also use here the semi-universal arguments. We'll see in a minute why. Okay, so that's the basic idea. What is our worst case t-hard problem? So what we want is just some language L that is decided by a Turing machine M in time t. And we want it to be worst case hard. So for any solver that is smaller than t to the epsilon, it fails to decide some x. Okay, but this x can be different for any solver. So how do we get this problem? And that's where the difference come in that we saw earlier. So in the uniform case, we don't need to assume anything. We can just use time hierarchy theorems. In the non-uniform case, that's where we need a complexity assumption. So we need to assume that for any constant c, if we look at all circuits of size n to the power of c, then there is some language that they can decide infinitely often. Okay, and this is our worst case hard problem, the exact language in P that they can decide. So now that we have a worst case hard problem, let's see how we construct the puzzles. So naively, we can just, the challenger can just send the worst case hard problem to the solver and ask it to solve it. And the solver can make the computation, okay, compute m on x for t steps. Okay, but it doesn't really work this way. So we have one problem here, which is that actually, as I said before, it's a worst case hard problem. So every solver has a different instance that it can't decide. So how can the challenger know which instance to choose? And the solution for this, so it was inspired by the work of Chankala and Vadal. There they show how to use fully homomorphic encryption to leverage worst case hardness into average case hardness. So what we do is actually we're going to do all of this under the encryption. Okay, so we use a fully homomorphic encryption scheme, and everything here is going to be under the encryption. And so the solver, in order to solve the puzzle, what it needs to do is it needs to homomorphically evaluate the computation of M on X for T steps. Okay, but now what will the challenger sample? What will it encrypt? So actually, it doesn't matter what it encrypts. Due to the security of the encryption scheme, the challenger can just encrypt the 0 string, and the solver can distinguish the case of the encryption of a 0 string and the encryption of the instance that is hard for this specific solver. Okay, and that's the way we get average case hardness. Okay, great. So we have average case hardness. Yes.
Verify can, because we know the secret, right? So I saw this a while ago. So solver still to verify, you need to open the encryption. What happens? So,
okay, so the question is how can we verify?
So you said it does not distinguish. It does not. So the solver does not distinguish. Maybe the verifier distinguish.
Okay, so why is it a problem if the verifier distinguishes?
By the out or easy depends on the. Don't smile at me. I don't remember. You remind me the issue. So it's competition. But my verifier is you can distinguish between what is inside the encryption, right? I don't see why hiding is enough.
Okay. What we are trying is that it will be difficult for the solver, not for the verifier. So
just wait one click. Nobody decrypts, right? The verifier decrypts for the not the verifier.
So okay, so the verifier doesn't decrypt.
How would you use semantic security?
No, the verifier does decrypt.
So no, actually the verifier doesn't
decrypt. Oh, okay. Just evaluation instead of running the circuit. Okay. I think.
Okay, let's see how we verify, and then we'll see if there's still a problem. So yeah, there was a question.
Right, you're trying to make it hard on the average.
Yes. Yeah. Okay. Yeah. So nobody decrypts.
You apologized before.
So the way we verify. That's where the semi-universal argument comes in. So we just ask the solver to send with its solution a proof that he actually evaluated the homomorphically evaluate the computation of M correctly. Okay. So yeah, so the challenger doesn't need to make the computation on its own in order to verify. It shouldn't decrypt because it won't work. I think it won't be sound if that's the way the challenger verifies. But we use the semi-universal argument, and now the challenger can verify. Okay, so that's our puzzle. And I just want to. So that's our puzzle. Yes.
So here we're really just using the semi-universal argument as a SNARG for P, right? Like with this, could we just use like our existing SNARG for P construction? We're just using the semi-universal argument as a SNARG for P here, right?
Yes, exactly. We don't need it to be universal because it needs to prove a computation that takes T steps.
Oh.
And it's the same T that we don't know any upper bound on. And actually, that's a great question because there is one problem in this puzzle, which is we use the semi-universal argument. When we use a semi-universal argument, what we get is some sort of semi-universal puzzle. And what I mean by that is that the soundness of the puzzle only holds if T is upper bounded by some polynomial. like in the semi-universal argument. So let's see the construction again and see whether it is a problem. Okay, so we asked the prover to solve a puzzle of difficulty t. And what we're trying to say is that if the adversary tries to make a statement that is bigger than itself, that it can't compute, then it won't be able to solve the puzzle. But as I said, in the universal language, we also have super polynomial t. So what if the adversary tries to make a statement with a super polynomial t? Then the soundness of the puzzle doesn't hold. We don't know, maybe the prover, the adversary might be able to solve it. It might be able to convince the verifier with its solution because the soundness doesn't hold. So, okay, so we use this semi-universal argument. And we got a semi-universal argument. It seems like we didn't do anything. Okay, but it's okay. There is a solution for this. So what we actually do in our construction is we ask the prover to solve all puzzles up to difficulty t. And now there will be some puzzle here in this row that is big enough, but not too big. So big enough in a sense that a polynomial adversary, the polynomial adversary can't solve it, okay? If it tries to make a statement that it cannot compute, there will be some puzzle here that it can solve. And it's not too big in the sense that its difficulty is still polynomial. So since the adversary is polynomial, I can just take the first puzzle that it can't compute, and its difficulty will still be polynomial. And now we can use our puzzle. Okay, great. So this is our construction. And now just a quick note about future directions. So there is an important and an interesting technique here of using puzzles to reduce super polynomial assumptions into polynomial assumptions. And so there is a question if it can be, if we can try this technique in different settings. So for example, there is also already a previous work of Bitansky and Solomon that uses a similar technique in the setting of leveraging leveled homomorphic encryption into fully homomorphic encryption. So they use puzzle to reduce the super polynomial assumptions into polynomial assumptions. There is a question if we can do use this technique in other places. Okay, that's it. Thank you.
Anna, anything more to say about the complexity dimension? Nothing particular.
I can ask more specific question.
Oh,
Is there no like separations between FHE and the kind of complexity theoretic assumptions that you made? Are there no separations or?
No. But we can't. FHE isn't enough for us. We need this extra assumption.
Okay.
Can you give just like a sentence of intuition about how forcing the prover to work with like the instance under FHE make worst case to average case?
Yes. So the idea is that the idea is that the solver is of size polynomial. Okay, so it can distinguish an encryption of a zero string from an encryption of the specific instance that it can solve. Okay, so we said that the solver that is too small, there will be some instance that it cannot solve. And now, when it gets the encryption of zero, if it is able to solve this encryption, it should also be able to solve the encryption of the instance that is hard for it. And if it won't be able, then we can use it to distinguish the two encryptions.
I see. That's very interesting. Thank you.
Okay.